So my talk is dedicated to some criticism of n-body simulations, and actually the point that is known for at least 20 years is the so-called Core-cusp problem, which is excuse me, I cannot change the slide. Just go errors.
Yeah, try with this.
Okay. Yes, just it's just slow. Okay, so what do we know about the central regions of dark matter profiles? There are several models. Of course, there is this isothermal profile and Navarro-Frank-White. Now, Einasto, at least a couple of years before, it was very popular. But n-body simulations of pure dark matter always give us something cuspy, which means that the density profile of cold dark matter in the center of a halo should be either infinite or at least very high. So the density of dark matter in the center of the halo should be very high. And as a result, its annihilation of the dark matter should be very intensive. But this is another topic. Now we're speaking about a bit different stuff. On the other hand, observations show that neither galaxy, especially for galaxies, at least some of them have a core in the center, which means that the density grows up to some limit, and then it remains almost constant. There is no cusp. And moreover, observations suggest that the multiplication of the central density of a galaxy on the core radius is more or less constant for various galaxies. If you look at this scheme, you will never see Paolo Salucci, because I removed his name because in order not to be accused in corruption. But actually, he should be in all this list because he is one of the he is the person who discovered this relationship, and he had also a large list of publications on this topic. So if we believe to observers and if we believe to n-body simulators, we can now say that the paradigm of cold dark matter is wrong because there is a clear contradiction. But in order to make this statement, we need to be sure that n-body simulations are also correct. And this is the point which I would like to discuss, because typically n-body simulators say that we all get approximately the same results there, and so these results are correct. But actually, typically they use the same, essentially the same algorithm. First. The second point is that they don't like to speak about difficulties of n-body simulations. Actually, they have weak points, of course. I should underline that I don't want to say that n-body simulations are useless or stupid or anything else, because actually it's the only way now to solve the large-scale structure formation. It's a very complex nonlinear task, and actually this is now probably the best way. The only message that I want to say is that we should not believe in the n-body simulations blindlessly. We should check every time if they are correct or not. First of all, they all use so-called tree algorithm, which means that if they want to calculate the gravitational potential of a system, at some point, they do not calculate it as a two-point potential of these point bodies. They use much faster algorithm, which is the following. They calculate, they divide all the space into cubes, initially into 8 cubes. And they calculate this parameter, which is represented over the picture. Actually, it estimates what mistake in gravitational acceleration we make if we substitute the real distribution of particles in the cube by a single point particle in the center of the cube. And this f is the parameter that you should set. The smaller this parameter is, the closer this algorithm to direct summation of potentials. But then it consumes more time. But anyway, this is not a precise, this is fast, but not a precise algorithm. The second point is that n-body simulations use quite a rather simple, fast, but not very precise method to calculate the particle orbit. These are just a result, these plots are taken from a paper where one of the best modern algorithms, Gadget 2, was presented. And they say that apparently that algorithm is much worse than this one. This is what is the task? Here they calculated the Keplerian case. So the precise solution is an ellipse which doesn't move. And they say that this algorithm is bad because the energy changes and the ellipse moves. And here only the ellipse rotates, which is unphysical, but yet the energy conserves, it's much better, and so on and so on. But you can see that even for one particle, the method is not very precise. This is the method of calculation of particle trajectories. But and we are going to discuss the Core-cusp problem. So we are interested in what is the smallest radius at which we can trust to n-body simulations. N-body simulators say that the only problem that we have is that we substitute tiny dark matter particles by massive bodies, test bodies, and therefore the collisional relaxation of these bodies is much more significant. So what do they do in order to estimate the radius of convergence of n-body simulations? They calculate the relaxation time of these collisions. This is an analytical task. You can find it in any book of cosmic dynamics, of star dynamics. This is the relaxation time of a system of n bodies, and this is the dynamical time at a radius. Here, the number of particles depends on radius, and the relaxation time depends on radius. The relaxation time, the dynamical time is defined like this. And so they There is a well-known work of Power et al. Of 2003 on which all these calculations are based. They performed a series of calculations, of simulations, and controlled until what radius the density profile doesn't change if we change the parameters of n-body codes. And they found that we can trust to n-body simulations until 1.7 relaxation times. It's very strange because it's almost 2 relaxation times, and still the profile is stable and it is not affected by the relaxation. But in some very respectable articles and works, even this criteria was used. And they even grounded that at 30 relaxation times, there is no effect. But the problem is that it is easy to show that if the particles collide, they can also form a stationary profile. But it is no longer defined by collisionless equation, but it is defined by collision equation. And but I will say more about this. This is now too early to say that. So what we did, we decided to do some things that actually should be made by simulators long ago. We performed a simple test. We set not this complex cosmological stuff, but we set a single halo, single spherically symmetric halo with spherically symmetric velocity distribution at each point. And for for Core-cusp profile, which I mentioned before, because the Core-cusp profile is almost like Navarro Frank White. It has the same cusp, but only the behavior at large distances is different. And for this profile, we have an analytical solution, how we should set particles in the phase space so that the profile is stable. And we can control, is it stable in simulations or not? What we found, we used 100,000 test bodies. It seems that it is not much, but actually in real n-body simulations, not many halos has more than 10,000 particles. And since we know everything about the system, we know its gravitational potential, we know everything, then we can, first of all, we set this A to be equal to 100 parsecs, and thus our task is defined, and the mass of the halo as 10⁹ solar masses. So it is approximately like Draco satellite before it was destroyed tidally. So we took something of a real system. The dynamical time is of the order of 1,000,000 years, and the relaxation time is of the order of 1,000,000,000 years. But since we know the system much better, we could control it better, because we know that there are integrals of motion. For instance, the energy of each particle and the angular momentum, because our gravitational potential of our halo is spherical and it is stationary. So we can control the behavior of these integrals of motion. Instead of energy, we use the maximum radius at which a particle can move from the center. And this parameter also should be constant for each particle. And the angular momentum should be constant. And we controlled how, in fact, this integrals of motion behave with time. First of all, we almost precisely reproduced the result of power, which was published in 2003. We found that really the profile remains stable until 2 relaxation times, then a core appears. It is true, but we used set of three parameters, which describes this tree algorithm. And we used another code, which is much slower, but much better in the sense that it used direct summation for the potential calculations. And we found that if we use the tree algorithm, we can almost precisely reproduce the power results. But if we use the precise summation, the core doesn't form. The cusp remains stable even after this period of time, which means that what Power and his co-authors, of course, considered as the moment when collisional relaxation becomes important, actually it is even created by another effect. It is created by the problems of tree algorithm and not by the collisions of the particles. It has nothing to do with the collisions of the particles. This is the first result that we have found. So this criterion has nothing much to do with reality. The second point is the following. A short remark. I will skip it. The second point is that here we have them we considered the particle and calculated the mean square deviation of the integral of motion divided by the for the momentum divided by the momentum corresponding to the sphere, to the radial orbit and to the circular orbit, and for a radii to the average radii. So we found that if we take a system of particles with the same radius, the average momentum of the system remains constant, but the particle, if we consider the integrals of motion of individual particles, they change very strongly. In a million years, it is something like 30% of the maximum angular momentum of they could have. And even the radius of particles change on approximately 30%, which means that particle efficient, that actually particles interact in these simulations because they exchange their momenta and their energy. It seems that, okay, we can ignore it. Why should we consider that? The average remains the same. But actually, if we consider, for instance, voila. If we consider this is the only slide of theory, first of all, a spherically symmetric hollow with an isotropic velocity distribution can be considered, can be described by a single function. So it is a fact that you can find a limit remain, for instance, and such, because And body simulators typically say that we cannot reproduce the velocity distribution of particles, but we can reproduce the density profile because our results are more or less the same. But it is impossible because actually this is an effect of both the distributions are described by the same function, by the velocity, by the distribution function in the phase space. In the particular case, when the function is spherically symmetric, this is just a simple function. And it is impossible to reproduce the density distribution reliably if you cannot reproduce the velocity distribution reliably. And what we found that the integrals of motion change. It is very important because if you have a collisionless system, its distribution function can be described as df over dt is 0. The distribution function remains the same. If there are collisions, you should substitute here the Fokker-Planck term describing the collisions. The coefficients of the Fokker-Planck term are this and this. This we found to be 0, but this is essentially not 0. The squares of integrals of motion change. It means that particles effectively interact. So the system behaves as a collisional one, and it is not clear if this cusp is formed by this non-physical effect or it is real. The point is that if we have an interaction between particles, it doesn't matter what was the reason, real physical interaction or numerical noise or such. But if the particles interact, they can also have some profiles with stationary density profile. And it is easy to show that in this case, there should be a profile which is close to Navarro-Frank White. So probably the collisions form the cusp. And so my conclusion is very simple, actually. I will skip this one. And because my time is over, of course, excuse me. But the point is that we should understand the n-body simulations much better in order to state that the cusps obtained with simulations are really correspond to something which should be in a collisionless system, and which should be in natural n-bodies, in natural dark matter halos. And that's actually the reason why we have this core-cusp contradiction for many years, and still we cannot make any decisive conclusion from this. Thank you. That's it.
So maybe I missed this on, you started your talk with the rho C RC is equal to constant. If I understand, you're criticizing the result, but that is just an observational fact, right? You just fit, so that has nothing to do with simulations. You just fit the data to density profiles and you calculate rho C and RC. And even that observation has been, if you talk to Del Popolo, he'll say it's not a constant. It increases, it has a slight logarithmic slope and all that. But anyway, independent of that, so that is just an observational statement. So I missed the criticism of the reason for criticism of that.
You mean that the profiles on the first slide?
No, second slide, the one where Paolo is an author on all those papers. So if I understand correctly, you were criticizing the result. But my point is that just an observational statement, nothing to do with simulations. But maybe I missed the reason.
What I criticize is that okay, we have really in simulations, we have cusps. But probably these cusps are created by some numerical effects. And that's why we cannot see these cusps everywhere. Because, okay, now there is this explanation that some baryonic matter can destroy cusps. But the point is that we can see cusps in the main problem where this core-cusp contradiction occurs is dwarf spheroidals with very small fraction of baryonic matter. And in some other objects where we have more baryons, there are maybe cusps. So there is apparently there is a contradiction, because in the objects that are almost free from baryons, we still have cores. That's the problem.
So if the tree algorithm isn't very good, but the direct summation is too expensive, is there something in between which is better?
Actually, you have found the weakest point of my talk, because I only criticize and I offer nothing. It's true. I don't know how to solve this problem, because I haven't mentioned many things about n-body simulations. For instance, if you read Binet-Tremaine book, it is written that actually this method is not stable in principle because of so-called Miller's instability. But still we may use it because statistically, the results for each single hollow are wrong, but statistically we may make some conclusions. For me, it sounds very strange. At least I'm sure that we need to make more tests of n-body codes, because the last serious test that I found was made almost 20 years ago. Since then, they test only the baryonic part. They put gas in the simulations, but now nobody already tests the pure dark matter. But I think even in the pure dark matter, there is a problem.
Do you think that there would be better algorithms? So the tree algorithm is not very good. The direct algorithm is too expensive.
No.
But can you imagine intermediate algorithms?
No. One of the simulations that we made was without tree algorithm. It was with direct summation, but this effect remained. I think, but I'm not sure, this is a result of very primitive algorithm of calculation of the orbits, but probably I am wrong. I have nothing to ground this statement, but something is wrong apparently, because integrals of motion change, and they change very significantly. In a million years, they change on 30%. I mean, on the average, the sum remains the same, but the particles just suffer random walking in the phase space. And actually, it is equal to interaction of particles. But the community ignores it, and they say that we want only the profile. We care not about the velocity distribution, but it cannot be true. Velocity distributions immediately transform into density profile. And here, okay, our density profile, by some unclear reasons for me, remain stable. But if you have a real simulations, this is just a model. But if you have a real simulations, can you actually believe in? Because there you cannot control it with mathematics.